already sent emails. We have everything you need to know. There's probably what wasn't announced is that there's going to be a
Okay, thank you for the invitation to speak here. So I'm going to talk about generalized CRF structures and pure spinor. So the context is that of generalized geometry. So say that M is a smooth finite dimensional manifold, and we denote by omega M differential forms, all of them. And this comes with an action, of course, of the group of diffeomorphisms of the underlying manifold, but also with the action of closed two forms by B-field transform. And so to accommodate that, so the right thing to do is to look at the generalized tangent bundle, the direct sum of the tangent and cotangent bundle. And there are various ways to think about this, and the one point of view that I find particularly useful is to think of sections of the generalized tangent bundle as endomorphisms, are linear endomorphisms of the R vector space of differential forms. And the way this is realized is in the usual way. So if I have a generalized vector x plus alpha, x is a vector, alpha is a form, I'm going to let it act on a form beta by contracting the vector with the form and taking the exterior product of alpha with the form beta. Right? So the thing to remember is that we're not just looking at endomorphisms that are linear over the ring of functions, of smooth functions on M, but we really think it is as are linear endomorphisms. And this will allows us to include other stuff in here, such as the RAM operator and so on, and we look at all of them at on the same footing. Okay, so we have this realization, and what happened? Oh. And this is the Clifford action, the one that we just described. And then now, as our linear operators, we have a natural graded commutators because these are operators acting on Z-graded R linear vector space. And so, for example, the commutator of X with the form alpha, here alpha is thought of as an operator, so it's acting by exterior multiplication, is given by just the contraction of the two. And now, within the space of R linear operator and differential forms, you had other things like the RAM operator, and so you can take various commutators of things in in this space. And one thing that you can do is to take the derived bracket with respect to the RAM operator, and as it's well known, this gives the so-called Dorfman bracket of two sections of the generalized tangent bundle. And in this language of operators on forms, you take first the commutator of this operator that acts by the Clifford action with the RAM operator. That gives you another R-linear operator. And then you commute the result with this other section of the generalized tangent bundle, and that's the Dorfman bracket. Likewise, you can define the generalized Lie derivative introduced by Hitchin, and that is given by taking that is an operator that acts on R-linear operators on forms, and the action is given by taking the Dorfman bracket with of x plus alpha with the argument. In other words, commuting with this commutator over here. Okay.
This definition is not clear that the Dorfman bracket is internal to T plus T star.
You're right. It is not. It is not clear a priori. It's just some R-linear endomorphisms. Then you have to show it that it's actually landing again in the generalized tangent bundle. Yes, that's a good point. Okay. All right. So now, as a warm up, let's look at classical F structures. Those were defined by Yano and collaborators back in the 60s. And these are endomorphisms of the usual tangent bundle. There's nothing generalized here. But unlike almost complex structures for which you have that they square to -1, right? Here we have something slightly more general. We have that applying this endomorphism 3 times is equal to minus applying it once. Okay, so certainly generalized, certainly almost complex structures are examples, but you have more possibilities. And one way to see this is that you can do the same thing as you do for complex structures. You can look at the square root of -1 eigenbundle of this endomorphism. It's clear from this condition that the eigenvalues must be 1, can only be 1, 0, and -1. And square root of -1, plus or minus square root of -1 and 0. Sorry. And so you look at the square root of -1. And then you can decompose the complexified tangent bundle as a direct sum of the square root of -1 eigenbundle minus square root of -1 eigenbundle, the complex conjugate, and the kernel. So with respect to almost complex structure, you have the possibility that this operator has a kernel. And then the integrability condition is again that L phi, the square root of -1 eigenbundle, is involutive with respect to the Dorfman bracket. And since these are just vectors, complexified vectors, the Dorfman bracket here is nothing but the usual commutator in the Lie algebra of vector fields, not the Lie algebra are linear endomorphisms on forms with respect to the commutator that we saw before. Yeah. Okay. Right. So if the kernel of phi, this endomorphism of the tangent bundle such that its cubed is equal to minus itself is 0. If this is invertible, then this is precisely an almost complex structure, and that requires the dimension of the underlying manifold to be even. And this is integrable if and only if is a complex structure. If the kernel is one-dimensional, this is what sometimes is called generalized, almost, not generalized, sorry. Well, it's also generalized, but that's not the name that was used in the classical literature at the time of Yano, but it's an almost contact structure. And in this case, the dimension is odd. And it's integrable if and only if phi is a CR structure. Now, one thing that was already worked out in the classical literature in the late 60s, early 70s, is the notion of normality of this classical F structure. So suppose that we have the composition that we have had before. So the complexified tangent bundle decomposes as the kernel of this operator phi on sections of the tangent bundle plus L phi. This was the square root of -1 eigenbundle and its complex conjugate. Right? And now suppose that we are in a situation where the kernel of phi admits a global frame. It's trivialization by a global frame. And let's denote a basis of this frame xc1, xck. And then you have the dual frame, eta 1, eta k. And then you see that you say that the pair consisting of the endomorphism phi together with this global frame xi I is normal if phi is integrable, so it's an integrable F structure, and moreover the generalized Lie derivative in modern language of phi with respect to the vectors in the global frame is equal to 0. And you can also rewrite this in this way. Now, in this case, you call this phi prime and xi prime I an F structure on M prime with a complemented frame. And there is a theorem of Morimoto, classical theorem of Morimoto, that says that under these conditions, you can construct an ordinary complex structure on the product of M and N prime by taking the sum of the F structures on the two sides, and then that, since there is a kernel, that doesn't give you an almost complex structure, so you have to add something, and having a frame allows you to do that. And a priori that gives you only an almost complex structure, and the result is that this is an actual complex structure if and only if the data that you have on the two manifolds M and prime gives you are normal. And the motivating example for Morimoto was an example of Calabi and Ekman, where they start with the usual embedding of S3 in C2, and they look at the usual hop vibration. And then they take two copies of S3. So they have now a base that is S2 cross S2. And now they have, so here you have S3 cross S3. And the fiber now is, of course, S1 cross S1. And now they have the freedom to define a complex structure on this torus. So there's a whole tau worth of choices. And once you do that, with S2, each copy of S2 having the usual CP1 structure, then this puts a complex structure on S3 cross S3. That was Calabi and Ekman's example, and Morimoto generalized to arbitrary product, and he realized that what really made the example of Calabi and Ekman work was this structure of normality. I got this. Okay, so now let's pass to the generalized situation. Let's fast forward to the 21st century. And now, what are we going to do? This definition is due to Vaisman. Now, instead of having an endomorphism of the tangent bundle was cubed is equal to negative itself, we're going to have an endomorphism of the generalized tangent bundle that, again, cubes to negative itself. And then we're going to ask it to be orthogonal in this sense, where here the commutators are commutators as operators, are linear operators on differential form, like we saw before. And in the paper I wrote on this subject, I find it useful to add an additional condition that wasn't there in Vaisman definition, which is what I call the split condition, is that, well, again, for this, from this condition here, you see that the eigenvalues can be plus or minus square root of -1 or 0. And so, in particular, you can have a kernel, and I require the kernel to have a signature kk with respect to the tautological product on T plus T star. I don't think this is a very important condition, but it does make a more clear connection with geometric intuition with the classical case. And also, all examples of generalized F structure that I'm aware of are in fact do in fact satisfy this split condition. Well, it's easy to construct a trivial example, but the geometrically motivated example all have this condition. Okay, so then we're going to do the same exact thing as we did before. We're going to look at the square root of -1 eigenbundle, and then we're looking at the composition of the complexified generalized tangent bundle as a direct sum of the kernel of phi plus the square root of -1 eigenbundle plus its complex conjugate. And again, Vaisman defines integrability, in his language, phi is a CRF structure. CR is for Cauchy-Riemann, F is referring to Yano's F structure. So a CRF structure if the square root of -1 eigenbundle is involutive with respect to the Dorfman bracket. Now here you really need the Dorfman bracket. In the previous case, in the classical case, this was just the Lie commutator of vector fields. This is now these are sections of the generalized tangent bundle. So the right thing to do is to look at the Dorfman bracket. Okay, so let's see some examples. First of all, you recover the classical case. If phi is a classical F structure, then you can construct a generalized F structure, capital Phi, by taking the direct sum of phi with minus phi star. And again, phi is integrable if and only if capital Phi is a generalized CRF structure in the sense of Vaisman. Moreover, just as in the classical case, if the kernel of capital Phi is equal to 0, then you have a generalized almost complex structure in the sense of Gualtieri, and this will be a generalized complex structure if and only if capital Phi is a generalized CRF structure. So we already see from these two examples that generalized CRF structures are common generalizations of classical F structures and generalized complex structures. And a sort of example is coming from contact geometry. So suppose that eta is a contact form. So eta wedge d eta to some power is a volume form. And then you can construct a generalized F structure with the properties that it annihilates the contact form, and its action on a vector field is given by the generalized Lie derivative with respect to the contact form of that vector field. Now, as it turns out, this is not a generalized CRF structure. So if you look at the Dorfman bracket of the square root of -1 eigenbundle with itself, this will not land into itself again. However, if you project the Dorfman bracket onto the image of phi, so if you disregard the pieces that land in the kernel of phi, then this is true. Then the result will be in L phi again. And so this is what I call the weak generalized CRF structure. Notice that if you have an honest CRF structure, then the projection onto IML will, of course, land here itself, because you have this decomposition here. So L phi is already in the image of phi. Yeah.
So L phi is always a Lie algebraic when it's integrable.
When it's integrable, yes.
In this case, is this sum with the kernel is an extension of that Lie algebraic.
Yes. So right. So if you it's an extension, but if you project onto the image, then you still have some kind of integrability condition. So this allows you to go beyond the generalized CRF structure and include geometrically interesting things like contact structures. If you stay within CRF structures, then the only thing that you can do is essentially cosymplectic, at least in codimension 1, it's cosymplectic structures as opposed to contact. Okay, so now let's look at normality. So suppose that we have a global frame phi is generalized F structure, and we have a global frame. An example is the theory of generalized almost contact structures due to Poon and Wade, where they, in that case, you're in codimension 1, so you have 2 sections of the kernel that they fix once and for all. And then you say that this datum is normal, just as in the classical case, if phi is the generalized CRF structure and the Lie derivative of EI phi is equal to 0, and the Lie derivative of each EJ with respect to EI is equal to 0. Then you get same structure on another manifold M. And then you have the following generalization of Morimoto's theorem that, again, you can look at the product of M and M prime. And you can construct a generalized almost complex structure given by phi and phi prime. That, of course, it's not enough because both have a kernel, so the direct sum will also have a kernel. But using the datum coming from the framing, you can fix that and extend this to an endomorphism that has no kernel. And this is one particular example, but as you can imagine already, that was the case for the Calabi-Ekman example. You actually have moduli. You have lots of possible choices of how to add this piece here. So that gives you lots of gives you families of examples, and the dimension of the family depends on how big the kernel was. And then the result is that this is a generalized complex structure if and only if the two data on the two sides were normal. They satisfied this condition. So this allows you to generate lots of interesting examples of generalized complex structures, starting with generalized CRF structures. And one example that I like is this. So you start with S3 embedded in C2, like Calabi and Ekman did. But now you deform C2 by adding the obvious holomorphic Poisson bivector. And that gives you a generalized CRF structure on S3. And when you apply this Morimoto, generalized Morimoto construction, then you end up with a holomorphic Poisson structure on the Calabi-Ekman space. And again, more than one. They are parameterized by some moduli here of how you pair the framing. So this is an example of application to generalized complex geometry. And Gomez and Talvacchia worked out somehow more special case, and then with Grandini we extended this to much more general framework that doesn't even require having global products. You can have even local products by complementary foliations and so on. But and we also discussed more detail this possible module. Yeah. So this is one possible application. Now, I want to discuss the interpretation of generalized CRF structures in terms of spinors, following what Hitchin did for generalized complex structures. So this is very useful, and it gives you an alternate point of view on generalized geometry that has various connections it's particularly natural from the point of view of physics. So let's look at first at the classical case. So suppose that you have phi is a generalized almost excuse me, almost complex structure. Then you can look at the square root of -1 eigenbundle in the generalized tangent bundle. And you can see that this has to be the annihilator with respect to the Clifford multiplication of some line in the space of forms, which is called a pure Spinor line following Hitchin and Gualtieri. And then the observation is that phi is integrable if and only if the action of the de Rham operator takes you from U0 to U1, where Um is the grading of differential forms that is given by multiplying the pure Spinor line with more and more sections of the negative square root of -1 eigenbundle. And so this gives you the composition of the de Rham operator that is obtained by looking at the behavior of the de Rham operator with respect to this grading of differential forms. And so, as it turns out, there will be a piece of the de Rham operator that increases the degree with respect to this grading, and increases degree by 1. And that is called del bar. And then you have a del operator that decreases the degree by 1. And you have that this is and if this if the manifold is so-called generalized Calabi-Yau, then you have that the del bar complex is quasi-isomorphic to the complex of the obtained by the full exterior algebra of the negative square root of -1 eigenbundle, where with the action is given by this operator dl phi that is constructed in the usual way. And now the nice thing here is that dl phi is an elliptic operator, and therefore the cohomology of this complex, can think it either way, is finite dimension. So the dimension of this cohomologies will be invariants of your generalized complex manifold. Okay, so now let's look at the generalized CRF structures. Can we do something like this? Can we have an interpretation of generalized CRF structures in terms of spinors? And as it turns out, the answer is yes, but there are a couple of twists. So if you start to generalize the F structure, remember that is an endomorphism of the generalized tangent bundle was cubed is equal to minus itself and is orthogonal. Then you can look at the square root of -1 eigenbundle, and as it turns out, this will also be the annihilator of some space of forms. However, unlike the generalized complex case, now this is not going to be a line, it's not going to be one-dimensional, it's going to have dimension 2k, where k is the dimension of the kernel. And these are spinors. And as you can, as one can check, then the generalized F structure is integrable. This is the generalized CRF structure, if and only if the RAM operator sends the space of forms that is annihilated by the square root of -1 eigenbundle to the direct sum of itself with U1. So you still have a grading of differential forms given by applying higher and higher exterior powers of the minus square root of -1 eigenbundles to U0. However, since U0 now is of higher dimensional, this decomposition is a little bit coarser. And one of the effects is that in the generalized complex case, we didn't have this U0, and the reason why we didn't have it was just by simple degree counting. We just had that U0 goes to U1. And here there's a slight twist that you also have to allow the possibility that now there is a piece of U0 that goes to itself. This already occurs in codimension 1. And there are other equivalent conditions. So in the generalized complex case, you have that a structure is integrable. If and only if one is the condition that we saw before, that the U0 is inside U1. Another condition is that you can have, if you look at the adjoint map of phi with respect to the commutators as are linear operators acting on forms. So if I apply this to an arbitrary form, that will square to minus the identity, right? But that doesn't require integrability, but integrability is equivalent to saying that this applied to the RAM operator also squares to minus the RAM operator. Right. So now for generalized CRF structures, you have that phi is integrable if and only if one is the condition that we have here, the U0 goes to U0 plus U1. And the equivalent of this will be that the adjoint of phi. Now again, if you apply this to forms, when you cube it, you get minus the adjoint applied to that form. And integrability is equivalent to saying that this also happens when you apply it to the RAM operator. So this, well, maybe I can write it like this, plus add phi d is equal to 0. A couple of other characterizations, but I think these are the most useful ones. Okay, so now you also have cohomology as for generalized complex structures. So if you remember from a few slides ago, in the case of generalized complex structure, you have the composition of the RAM operator into del and del bar, and they increase and decrease the degree. Here is an unfortunate typo. This should be just del, not del bar. But the main feature for generalized CRF structure is that now you have an extra piece, delta, that keeps the degree the same and corresponds to the kernel of phi, essentially. As a result, in general, DL phi is not elliptic. The analog of what we had for generalized complex structure is not elliptic, and therefore this cohomology is not necessarily finite dimensional. It would be interesting to understand this issue better when exactly you get finite dimensional cohomology. I don't know the answer. And one thing that you can do with this decomposition is to use it to study deformations of CRF structures in analogy with what you do with generalized complex structures. So if phi is a generalized CRF structure, then you can look at epsilon as section of the exterior square of the negative square root of -1 eigenbundle. And out of that, you can construct a putative infinitesimal deformation as an F structure. And then you want to understand when this deformation will give you something that is integrable again. And this is the effect that the deformation has on the spinors. This is same as what happens in the generalized complex case. But then now when you study the integrability condition, now you have kind of Kodara-Spencer type of equations, and the main difference with the usual case is now instead of having just one equation, the Maurer-Cartan equation, you also have an extra equation that gives you compatibility with the third, well, here's the second, but the new piece in the decomposition of the de Rham operator, the one that preserves the grading. Okay. Another thing that this is useful for, the Spinor formalism is useful for, is to study T-duality in the BM setting. So now you have M and M prime that are fibrations with fiber, with torus fiber, and you possibly add 3-form flux. And now if you pick a form F, a 2-form F on the fiber product of M and N prime over B, that is non-degenerate and it satisfies this condition. In particular, if you don't have, if H and H prime are 0, then this has to be closed. And then you have this chain map that is given by fermionic Fourier transform. So you take a form here and you multiply with e to the f, and then you integrate over the fiber, and this will give you from here. It turns out this is a chain map, and now this makes it easy to transfer generalized CRF structure on across T-duality, because now all you have to do is to pick your spinor space. Right? It's no longer a line, but U0. That was annihilator is the square root of -1 eigenbundle. and then you apply this map here, and you'll get another space of forms. And it turns out that the annihilator will be the square root of -1 bundle of another generalized F-structure. And since this is a chain map, then the condition of integrability written in this way for generalized CRF-structures is going to be satisfied automatically. So you have the T-duality clearly maps generalized CRF structures to generalized CRF structures. This also follows from the Gualtieri-Cavalcanti point of view that that this map gives an isomorphism of current algebroids, and then using the original Vaisman definition. But the advantage here is that not only you have that this is sends generalized CRF structure to generalized CRF structure, but the map is straightforward. It's just a very easy calculation to see what goes to what. Okay, so now the last part of the talk, I want to talk about some application with something that I work with Raimundo Heluani here. And so we can look at the sigma model with target a manifold, and you can think one way to think of this is in terms of the free super loop space, so the equivalent of the free loop space, but now you have maps from a super circle to your manifold M, and this will decomposes with respect to the possible windings of that circle, and those are labeled by conjugacy classes of the fundamental group. And so there's a framework developed by Heluani and Zabzin of Hamiltonian quantization of the sigma model, you look at the cotangent bundle of this super loop space, and it comes with the canonical Poisson bracket, and as it turns out, its quantization lead to the chiral-de-Rham complex of the underlying manifold. It's a sheaf of super vertex algebras. I think you're going to hear more about this during the rest of the workshop. But one thing that Heluani and Zabzin pointed out is that generalized complex structures on M corresponds to action of the n equals to 2 superconformal algebra acting on chiral-de-Rham. And then this is just the kinematics of the sigma model, and then you can choose your Hamiltonian and have dynamics as well. So it's an alternate point of view with respect to the textbook presentation in physics books of the sigma model, which is based on the Lagrangian formalism. Basic example is that of the torus. In this case, the components, the winding components in which the loop space breaks into is labeled just by the fundamental group. You don't have conjugacy classes because the fundamental group is Zn, which is commutative. And then when you quantize, you get a copy of the chiral-de-Rham complex for each winding. And there is an alternate point of view that is given by Hall's double field theory, that is to account for the windings by looking instead of at the loops, the super loop space with target a manifold of twice the dimension, that is the product of the torus with its dual. Then this gives rise to a super lattice vertex algebra, and this gives you an alternate derivation of the textbook superconformal field theory that is associated to a torus. Now, things are a little bit more difficult when you look at Nil manifolds, and the simplest example is the Heisenberg Nilmanifold. Three-dimensional is the simplest. And so this is just a quotient of the real Heisenberg group of 3x3 matrices with 1 along the diagonal and 0 below, quotiented by the integer subgroup. And now when you try to quantize that, you run into some problem because the fundamental group is not commutative, and so it's not clear how to use vertex operator to take you from one winding sector to another. But instead you can do something, you can use double field theory and look instead at maps from the supercircle to this double twisted torus, which would be a 6-dimensional Nil manifold, and that's what we did with Raimundo. And now it turns out that it's not quite a vertex algebra because you have this dilogarithmic singularities. Nevertheless, there is a factorization structure that has some interesting properties. You recover the pentagonal identity of the logarithms. But in any case, you have manifest T-dualities of the sigma model we targeted the Heisenberg Nilmanifold with torus with the 3 flux, and similar arguments were found by physicists shortly after, and then later Linshaw and Mathai also look at the same issue, but from a slightly different point of view. And I should also say that Juan Villarreal, a student of Raimundo, recently worked out some additional cases. And so now you can start look at generalized complex structures on these Nil manifolds. Now, for generalized complex structure, you have to have even dimensionality, and so one easy way to do this is to cross with S1. And then you see that as in the case of simply connected manifolds or for tori, where where generalized complex structures corresponded to n equals to actions of the n equals to 2 superconformal algebra on chiral-Derham. Now here you have a little bit more than chiral-Derham. You have this this other structure that comes from this double twisted torus, but nevertheless you have actions of the n equals to superconformal algebra on whatever the quantization is. And then you have manifest T-duality or mirror symmetry if you choose the direction to T-dualize correctly, with a 4-dimensional torus twisted by a 3-form flux. And at the end of the day, you have a canonical identification of global moduli of equivariant generalized complex structures on the Gerby 4-dimensional torus. This is actually the case that is easiest to work out because it's more symmetric. And equivariant orthogonal complex structures on the double geometry, this 8-dimensional Nil manifold. So notice that we got from generalized complex structure here to honest complex structure that has to be orthogonal with the tautological pairing that you have there. And then you have equivariant generalized complex structure on the Heisenberg manifold M, the product of the Heisenberg manifold with this one. And then you also have n equals to 2 superconformal actions on the quantum sigma model. Now, the reason why we had to why we added this factor of S1 here is because we want a generalized complex structure. That's what we wanted to do. But if you're willing to work with the generalized CRF structure, then you don't need to cross with S1. You can work directly with the odd dimensional manifold. And that's something I did with my student Sarah Williams. So now you can use, you can see how generalized CRF structures on M act on CDR, as more precisely the the quantization of the sigma model here. And now we get a similar story. You look at the double twisted torus, like the double field theory tells us to do, and then you have manifest T-duality between generalized CRF structures on the Heisenberg Nilmanifold and generalized CRF structure on this 3 torus twisted by the 3-form flux. And you get, like we had before, canonical identification of global moduli of equivariant generalized CRF structures on the 3 torus with the 3-form flux, and equivariant orthogonal classical integrable F structures on M, and equivariant generalized CRF structures on the Heisenberg Nilmanifold. And you can also look at the actions. So the actions here, they tend to give you again representations of the n equals to 2 superconformal algebra. If you go to higher dimension, you can also have things. Situations in which the current, the supercurrent has 0 OPE with itself, depending on how it sits with respect to the Ram operator. But in this case, that everything works as before. All right, and then I'll stop here. Thank you. Yes.
So you have, of course, some spectrum generating superalgebra. Which kind of spectrum generating? Is it finitely superalgebra or is it finitely superalgebra?
So for the 4-dimensional or the 3-dimensional case,
Just the base manifold is just S1/1, so it's a word line.
so you mean in general, not for the here? Yes. So what is the
Which kind of spectrum generating superalgebra do you have? Is it finitely superalgebra or not finite?
I'm not sure. So in the case of the 3-dimensional Heisenberg group, you have the part of that comes from chiral de Ram has a structural affine of affine algebra, but that's I don't know in general.
These are not sigma models on S11. So these are 2-dimensional sigma models. It's just that he's just taking a slice of the worksheet. So the sigma model is not going to be an S11. The least superalgebra that's there is infinite dimensional. So the same.
You could look at the case where the target is.
No, but he's talking about just the source. And
I see. Yeah, okay.
yeah.
Yes.
So my question is more on the speculative side. I suppose that you define the metric in the case of your Spinors structure as usual by pairing, right?
Yes, you have the Mukai pairing. That's what people look at.
But let's suppose that you really are interested in some, let's say, metric that comes from physics, like for example a solution of the Einstein equations.
Mm-hmm.
So could you comment on this case?
So you said that you could look at different pairings for in between the spinors. Yeah, I think that's definitely an interesting case. So this has been looked at for generalized complex structures. When you have extra structure like a metric, then you have this thing. And I think it would be very natural to look at it in the case of generalized CRF structure. But honestly, I haven't thought about it. But yes, that's a very good point. Yeah.
here you mentioned about integrability.
Mhm.
Is there any connection with the nonlinear evolution equation in PDE? That integrability means that you have an exact solution instead of numerical. Is it different notion here?
As far as I know, there's no direct link, but here integrability is in the sense of Frobenius theorem that you can integrate a distribution to an actual submanifold. I think that's where the terminology comes from. Yeah.
So I have two quick questions. So what is for the CRF side, what is the Calabi-Yau condition? Is it unimodularity of the same Liège-Roy?
It's not entirely clear. So there is so the natural thing would be to look at, I think, generalized Sazakian manifolds, but nobody really knows what those are. So Vaisman has a definition, but there are other definitions around. And I think that the spinorial formalism could provide a more conceptual approach to that. But I think the question is, what theorems can you prove about it, or if you have motivations from physics? Yeah, there are a few things that one can try.
But a related question is that when we looked at this four-dimensional target, because not because I want to generalize complex structures, but I want to generalize Calabi-Yau structure. I wanted n equals 2 superconformal structures. And to have n equals 2 superconformal structure, I needed Calabi-Yau structures, right?
Yeah, but
now you're claiming that these algebras also give you n equals 2?
Yeah, so you have, but I think this is because it's parallelizable, so it's kind
Yeah,
of,
so automatically you're
yeah.
gonna get the Calabi-Yau condition.
Right.
But you seem to claim that the CRF structures also give you n equals 2 as a superconformal structure.
For the three-dimensional Heisenberg manifold, yes, but in general, I think that's stuff for future work.
A more general case would be if you can have a CRFK structure in the pure spinor approach.
CRFK?
Yes, for Keller.
Oh,
For Keller.
so you mean two compatible CRF structures? Yeah. So that's something that the people have looked at recently. So yes, so there is a theory of generalized co-Keller structures, but it does, while you can prove some theorems about it, it seems that the right thing to do should be, or at least the closer analog to the Calabi-Yau condition would be to look at generalized Sazakian structure, and in that case the compatibility is a little bit more complicated. Yeah. Yeah.
There's no more questions, then let's thank Marco again.